And now the example for this convolution definition is a little bit long, but we have done part of that. That's again the dam oscillator, but now it's not homogeneous. Last time we did was the homogeneous equation. Now we add the forcing term, and this is the forcing term that will require a convolution. So the equation, the left-hand side is the same, so minus x double prime. The second derivative is the acceleration. T plus the damping term b, coefficient b, and then x pi is the velocity. Plus k. K is like a spring constant. Now you add the right-hand side, the forcing function as a function of t. Okay, and then the initial condition is simplified now to x 0 is 0. Just start from 0 location, and then the velocity is also 0. So that make it a little simpler. But then because of the right-hand side, it's still need the convolution to get the solution. Okay, then now you do the Laplace transform on both sides, each term. So now with all these initial conditions, that becomes trivial. So it's m, this becomes s squared, and the little x is the Laplace transform of capital X, and plus b s x equals now this Laplace transform of f, capital F is little f. Okay. So this is Laplace transform of capital. Okay. And now the solution is straightforward. And x is this s divided by s squared plus b. Okay. And so now obviously the capital X your solution should be the inverse transform of this one. Okay. Now the complication is that this is a product of two Laplace transforms. One is little s, the other is this one, right? And then what you do is first figure out what is the inverse transform of this one, and that is what we did before. And what we did is write this as a complete square. Right, that's it. I think instead of doing it again, I just copy from the textbook. We did the complete square before, so it's basically the same. E over 2m squared, and then plus omega 1 squared. And this omega 1 squared is defined as omega 0 squared minus b squared over 4m squared. This omega 0 squared is just intrinsic frequency just k. Okay. So now with the complete square like that we did before, and the Laplace transform, inverse Laplace transform of that is straightforward. So, or you can say this one. So, so let's just write more explicitly. So Laplace transform of f is little f. Okay, and for this one, the Laplace transform of the variable e to the minus b over 2m t sine this one is this one. This is I should say this is multiplied by omega. Yeah, this is like a sine Laplace transform of sine, but you shift it, a little bit in the transform variable. Whatever you shift, you multiply by the exponential function using that shift as your argument with the negative sign. Okay. So that is the two Laplace transform. So other than this m, the mass, basically, yeah, we basically have everything because now all we need to do is do a convolution of these two, this one and that one, right? Because this is the product of this Laplace transform. So inverse Laplace transform will be the convolution between this one and that one, right? So x to xt would be you have the m function, yeah, 1 over m. Yeah, I was thinking about this convolution between. Yeah, this one you can divide the omega 1, omega 1 to the other side, and then that becomes the convolution between this one divided by omega 1, and then we have because that this one doesn't have omega 1, so or I can write down multiply omega 1 and divide by omega. So this one is this one. Okay. All right. So we need the omega 1 factor in the denominator. Now it is the convolution. Now the convolution doesn't depend on the order. So you can either which one you shift the argument doesn't matter. So it's 0 to t, and if you use f, capital F as shifted the arguments to t minus whatever your textbook variable. And then the other is just this one, which is multiplied by e to the minus b. The integration variable is z over 2m sine omega 1 c. Okay, so that would be the formal solution in terms of the convolution. Right? Yeah. For Laplace convolution is 0 to t. And what I did before I do this example, I said I can extend it to minus infinity to infinity. And as long as we remember these two functions are only defined for positive t, and for negative t, they should be 0. Then doesn't matter. Then you can integrate minus infinity to infinity. Doesn't matter. Fourier transform, you have minus infinity to infinity. Yeah, because in Fourier transform we define as you integrate over all time to get the Fourier transform. Okay. And like Laplace transform will only integrate over positive t. That's the main difference that that give you this difference in the convolution. But if we extend everything to the negative t with a step function that Q off all the negative t dependency, you can change it to negative infinity. That doesn't matter. But well, for this example, we just write the explicit dependency out without all the step function, just 0 to t. Okay, and so this is a general formula. Depends on an unknown function, the driving function f, capital F, right? And the well, it depends on whatever the f is. The first example for this capital F is trivial. It's just a impulse ft is t just a constant times delta t. But if you use that, this is just example. Right, and you just substitute this into here. That becomes a delta t, a capital P times delta t minus z. You integrate it over z, right? Then for using the property of delta function, basically changing all the argument or integram, all the dependent of z becomes t, so all the z becomes t, and that would be the integral. Except that now you have one subtlety that if you change that to a negative delta function, the argument is 0, is t minus z is 0, and you integrate with z, that is exactly when z equal to t, which is exactly the upper limit. And that could means a certainty because now you're integrating. So we keep the whole delta function, or half of the delta function, and that is a ambiguity. And you can resolve that by slightly shifting the delta function. So you can say that this impulse is not exactly at 0. So when you have delta function, you say that at t equals 0, you give it an impulse. So just a kick of the whatever the mass, right? That's the impulse. You're saying that at t equals 0, exactly nothing happened, but just slightly after the initial point, 0, you give it a kick. So you can say this minus, you kick it at slightly off 0, right? If you do it like that, you substitute this, then that becomes a delta. That becomes a delta t minus z minus 0 plus. So that argument goes to 0 at t minus a little bit, right? So it's not exactly at the upper limit. It's a little bit before the upper limit. So then you can keep the whole delta function, right? If you do it like that, so you define something like that, then obviously x is just t over one. Just everything changed to t. Z changed to t. Okay, that's this is kind of preview, except this ambiguity that we resolved by this way. Right. The next example is a little bit more involved because it involves a partial fraction. So we can find some space for that. All right. I don't think we need those. Don't need this. Next example, the second example, I don't know how we'll finish discussing everything, but this capital F is constant times sinusoidal force. This is sinusoidal driving, the sine omega t. So this omega can be it's just a variable is unrelated to. I mean, you can choose to close this omega 1 or omega 0, but it doesn't have to be any arbitrary omega, right? And now this little f is the Laplace transform of capital F. which is just look at the table. This is I think this is our K, or originally it's a K in the table. So it's omega divided by S squared plus omega squared. So that should be, that's this little f, right? And so the one way we could do is just use the sine function and do the convolution. So that's the omega t, and that probably is doable. That probably is doable, but your text will use another method. Just go back to the x equation. Now with the f, with the little f, just writing out explicitly. So this little x before we get to this one, including all the variable f0 omega. There's m, and then this one omega s squared plus omega squared, and times whatever the other one that produces basically this one. That's omega s plus omega 2m squared plus omega 1 squared. Right. And then the way to do it is get the partial fraction. So your two factors, h is 1 over something square of the involving square of s, or s plus something square. You can do a partial fraction and get to two terms. Other than this or this coefficient. So your text will use 8 pi s 8 pi. These are unknown function you try to solve. And then there's c pi s d pi, and whatever that is. And once you solve all these unknown coefficient, a pi, b pi, c pi, d pi, then you do a inverse Laplace transform. Now you know you're not using convolution, but just like what we did look up, because all these are known transforms. So s divided by this, that will give you the cosine, right? This will give you the sine, right? And these are similar cosine sine and multiplied by this exponential factor, right? And that is fine. So you can do it that way. And one simplification, if you are only looking at the steady state or quasi-steady state, you drive it, and so that initially you have some what we call the transient, but that will decay away due to this exponential factor. There's e to the minus bt over 2m. This will go away in time. So all these are coming from the second term because of this shift in the s, right? So the second term will produce an exponential function in front. So all this will damp away. There's sooner or later this one will damp away. So only the quasi-steady state or the whatever they call it. It's coming from this. So you only need to solve A prime and B prime for the what do we call it?
So which means the second term comes zero. This one.
Second term?
Yeah,
it's not zero. It's just whatever you get the inverse Laplace transform will have an exponential factor like that. And this exponential factor will go to zero for large t. So basically, if you are interested in the long time behavior or asymptotic behavior, all this will go away. All this, the inverse Laplace transform due to the second term will go away due to this exponential factor. Of course, if the full solution involved this, if you need the full solution, you need to solve for C prime and D prime also. But solving for A prime, I mean, it's straightforward. You just need to multiply this denominator, right? And this one multiplied by this one plus this one multiplied by this one, and with 4 unknowns coefficient, and that is doable. Right? So yeah, you have a cubic power of everything. A cubic power in S, a polynomial involving up to S cubed, right? Then you have four terms, and you have 4 unknown, and you can in principle solve that, and then get to the coefficient. Right, that in principle is doable, but I don't think we should spend the time struggling with this. But all the solutions. I mean, it's not the third order equation. It's just after you just multiply all the s power polynomials, just all the coefficient will be 0, except the last one. Last one should be 1, right? Because you go back to 1, and then solve for all the 4 and then. That is doable, but I won't do it here. And once you get the A prime and B prime, and that just give you the cosine term and sine term. And then the frequency is this driving frequency, not involving omega 1, omega sub 1, omega sub 0. It's not good. It's not oscillating in omega sub 0 and omega sub 1. That's due to this. What is what? This one? This is the original is on the right hand side of the reference. This is capital F. Is the driving term. You have an oscillator, damp oscillator. You drive it on the with some force. This is basically a force. The dimension is
the variable S.
Pi is S. Sorry, I don't get the question.
She's asking what is the variable S? What does the variable S mean here?
What is S mean?
Yeah.
In the Laplace transform, what is S means? S is like yeah. It's the dimension of S is also inverse time. So you can think about it like a frequency, right? So in Fourier transform, obviously, if you are the function is a function of time, then you do a Fourier transform in time. Then the variable for the Fourier transform is omega. We usually use omega. It's also a frequency. So this S is also has the function is function of time, then this S is also like the frequency, but then you can see this imaginary frequency that's involving the imaginary part. We'll get to more. This will become more apparent when we discuss the integral formula for inverse transform. But so this Laplace transform defines integrate from 0 to infinity minus st, right? Right. So this is a function of s. You integrate t out, and what is left is s. Just by this product s times t should be a dimensionless number. So t, if t is time, then s has the dimension of 1 over t, 1 over time, or you can say it's like a frequency, or because of the nature that unlike the Fourier transform, you have the either plus or minus omega t depends on it's imaginary of this I omega. And in that case, you can think of this like either a growth rate or a damping rate, depends on the sign of S. is it's something like that. You ask about the physical meaning of this S variable. Okay. And you can see from this all this formula also, like S squared plus omega. Omega, if omega is a frequency, then S is also a frequency, dimension of a frequency. S squared plus. Is that okay? So if you think about it this way, see how much time I have. So I'm not going through the rest of the example. It's just because I haven't solved for A prime and B prime. I mean, your textbook gave you all the formulas. You can read about that, and the physics is you talk about that probably in undergraduate physics, like the physics of resonance and all that. So you tune this omega. The resonant frequency is not exactly this omega 0 and omega 1 due to this damping. So it's cycle. If B is small, it's just cycle shift from either omega 0 or omega 1. Okay, but